The world of energy is changing nowadays, and we need to face the necessity to shift away from fossil fuel towards renewable energy sources. This aspect, together with the advance in the field of ICT, is moving all of us toward the smart grid, a grid that will use technology to improve its resilience and increase the service for the customer. This evolution, however, needs to take into account different challenges, such as the management of renewable energy sources, the distributed generation, and the increase of power demand from electric vehicles. In addition to that, new actors and new business opportunities will enter in the energy market. I'm Matteo Orlando, and my research at Politecnico di Torino focuses exactly on some of these aspects that I will briefly explain in this video. PV panels plays a crucial role in this shift from fossil fuel towards renewable energy sources due to their decreasing cost of their technologies. They also enable the appearance of new actors in the smart grid scenario, such as the prosumer, which are users that are both able to consume and produce energy to sell to the grid, and aggregators that, as the name suggests, aggregate the power demand and the power offer of multiple prosumer. For this reason, one of the topics of my research is the economic analysis of PV system installation, to analyze multiple possible panel configuration in order to provide a tool which enables prosumer and aggregator to maximize the return on investment. In my first work, I used yearly weather data and GIS technology to provide unusual but optimized panel placement in order to improve the power generation and avoid the shading effect, which can reduce the power production of PV panels installation. Starting from this framework, we wanted to upscale our vision, going from the perspective of the prosumer and his single roof towards the perspective of an energy aggregator and taking into account a whole district. To do so, we created a pipeline which were able to extract from satellite images the surfaces available for the installation of PV panels, and then calculate the estimated power production in order to find the optimal placement. To do so, however, we needed to take into account some new constraints, such as the possibility to connect panels placed on contiguous roof, but to avoid the connection of panels located on different sides, we were able to obtain optimal placement for panels on the roof of the whole district, together with analysis of the impact of the number of panels on the power production with cost and benefit. This because not always placing the maximum amount of panels can be the best choice for an energy aggregators. In order to have a proper smart grid, we need to increase the metering and automation capability of the grid to increase its resilience. Nowadays meters are mainly used for billing, and the automation of the grid is extremely low. In order to solve this issue, we proposed a three-phase smart meter prototype together with a smart metering architecture, capable of provide automation for outage management and provide communication infrastructure in order to perform cloud computing, edge computing, and fog computing. The prototype is composed by a Raspberry Pi and a data acquisition board and uses REST and MQTT communication. Together with HDMI, it's able to perform self-configuration and auto-update procedure, and is also able to run fault detection, fault location, and state estimation algorithm. External service can also be included in the advanced metering infrastructure. Both the prototype and the advanced metering infrastructure were tested using co-simulation technique. Real-time simulators were used to simulate the behavior of the real electric network, and a metropolitan area network simulator were used to test the communication part. All the tests were performed using hardware-in-the-loop technique. With this test, we were able to demonstrate the capability of the meter that was able to have a fast fault detection and location, reducing the amount of time needed to re-energize the network from the 40 minutes needed at minimum nowadays to only 10 seconds. We were also able to assess the resilience to the network congestion of the whole infrastructure.